Hello, everyone. Today we're going to look at the fundamental theorem of calculus. So we're going to do this in two different parts. All right. So the first part of the theorem says is if I take the derivative of an antiderivative, so remember an antiderivative is big F, if I take the derivative of that, this is the same thing as saying I'm taking the derivative of the integral from a to x over a function. So this function t doesn't mean anything. We call it a dummy variable. It's just a placeholder for right now. Then it's equal to the original function. So what this theorem says is if I take the derivative of an antiderivative, I'm back to where I started. I'm at the original function. So let's look at a few examples of this. Right. My first example, I have y equals a to the x of t to the third plus 1 dt. So if I take the derivative of this, then I'm taking the derivative from a to x of t to the third plus 1 dt. And what this is saying is the derivative and the the derivative and the integral basically canceling out. So all I'm doing is bringing us back to the original function. So I just have x to the third plus 1. So as long as it's in this form that I gave you from the theorem, all you have to do is plug in x. If it's not, then we're going to have to do a little extra work. So let's say we have something like this. So I have x as my lower limit, 5 is my upper limit, and we have 3t e to the t, something like that. Okay, and this is dt. And we want to find dy dx, but first, we don't have it in the form that we want. We have x at the bottom instead of the top limit. So remember, if we want to flip limits, all I have to do is multiply by a negative. So that would put the x on the top, 5 on the bottom. And then when I take the derivative, I can just plug in x. So I have minus 3x e to the x. So as long as if we have any constant as the lower limit, x as the upper limit, we just plug in x. The one caveat is if I have something like this. I have a constant at the bottom, but I have a function at the top. Say I have this. Y equals the integral of 1 over x squared e to the t dt. So what I'm going to do is I'm going to write this as 1 over u of e to the t dt. And we're going to say u is equal to x squared. Okay. So what I'm doing is when I take dy dx, or y prime, whatever we want to call it, I'm saying it's the same thing as dy du over du dx, which is the chain rule. So dy du times du dx is dy dx. The du's would cancel out, but now I can take the derivative with respect to u. So now when I take dy dx, this is the same thing as the derivative with respect to u of 1 to u of e to the t dt times du dx. So this is this part. And then we have to multiply by an extra du dx. But what is du dx? It's the derivative of u with respect to x. So it's 2x. So what this is telling us is, I showed a lot of work to get here, but I can just plug in whatever my function is. So in this case, I have e to the u times the u dx is 2x. So this is just e to the u times 2x. And we said u is x squared. So we have e to the x times e to the x squared times 2x. So what I could have done originally is if I just plug in the x squared, if I'm back at this step, if I plug in the x squared, if I ever have a function that's not just x, all I have to do when I plug it in is multiply by the derivative of that function. If it's x, we're just multiplying by 1, so we're actually doing that anyways. But we always have to multiply by the derivative of that function. So for the fundamental theorem part 1, those are the 3 possible cases that we could see. Let's take a look at part 2. What part 2 tells us is if we have a function with a lower and an upper limit of f of x dx, this is the same thing as f of b minus f of a. Meaning I can plug in my lower limit and my upper limit. Sorry, my upper limit, then my lower limit. And then we subtract those. So if we want an example, let's say we have the integral from 1 to 2 of 1 over x dx. Right? We know the integral of 1 over x dx. It's just the natural log with the absolute value of it. So what we can say is this is the natural log of the absolute value of x. And we're going to evaluate at 1 and 2. So that's where this piece comes in. I'm taking the bigger number, the upper limit, and I'm plugging it in. So the natural log of 2, I can drop the absolute value because natural log is positive, or 2 is positive, and then minus the natural log of 1, also drop the absolute value, 1 is positive, and then the natural log of 1 is 0. So this is just the ln of 2. Okay, let's look at another one. Let's say we have 2, 3, x squared dx. Okay, so if we have x squared, then the antiderivative, so x to the third over 3, and we're going to evaluate at 2 and 3, meaning I'm going to plug in my 3 first. I have 3 to the third divided by 3 minus 2 to the third divided by 3. If we wanted to simplify, this is 27 over 3 minus 8 over 3, which would give me 19 over 3. Let's try one more. Let's say I have 1 and 0. Let's just say we have x dx. Make it nice and easy. So if I have x dx, we know the antiderivative would be x squared over 2, but I can't do that quite yet, since my limits are upside down. I always need my lower limit on the bottom. So I could rewrite this as negative 0 to 1 of x dx. Now I can solve it. So I have negative, I add 1 to the power, divide by that number, and I evaluate at 0 and 1. So I have negative 1 squared, or the 1 is squared times the negative, and then divided by 2. And then I don't really need to plug in 0, because 0 squared is 0. All right, that's going to be it for the fundamental theorem. I hope everyone has a great day.